Hi, welcome to my presentation. I'm Byung-Ju Kim, the first author of this paper, Debiasing Neural Networks with Estimated Offset for Class Imbalanced Learning. In this presentation, I'm going to present our idea and its geometrical interpretation. I'm not going to present our experimental results, so if you want to know detailed experimental results, please refer our paper and come visit to the online session to ask any questions. So let me start. First, I'll introduce the class imbalanced learning. What is class imbalanced learning? The objective of the class imbalanced learning is to train an algorithm using data with imbalanced distribution. In this paper, the algorithm is a convolutional neural network. As you can see in the illustration, class 1 has few data samples, while class 2 has a lot of samples. When the data has imbalanced distribution, the decision boundary is drawn close to the minority classes. It is a very natural phenomenon because each sample from class 2 would push the decision boundary toward the center of class 1. As its result, majority class has larger margin than the minority classes. The disparity in margin means that the deep model has learned the prior knowledge. We want to fix this. We want to draw the decision boundary in the middle of each pair of classes. In other words, we want to build a classifier without prior knowledge. Before we go further, let me introduce a simple linear algebra. When we train a neural network for classification, we are training discriminative classifier. The discriminative classifier can be converted into generative classifier without additional training process. Using Gaussian discriminative analysis, we can calculate the closed form solution for the weight vectors and offsets. For more details, please see the reference. However, when we train a deep neural network, we do not calculate them. We just parameterize and train the weight vectors and offsets. So we consider that the trained values of vectors and offsets are representing the closed form solution. Between weight vectors and offsets, in this paper, we focus on the offsets. We can decompose the offset into two terms, and the first term is representing the prior information. The plot is the trained offset value for each class. You can easily notice that they are showing an evident trend. The offset value for more frequent class has larger value than the offset value for least frequent class. This is exactly what we want to fix. We don't want the prior information being in the trained offset value. To this end, we define empirical offset. As you can see, the prior information is removed. Since the training process contains the prior information, we cannot obtain this by training. We calculate it. So we calculated using trained weight vectors and feature mean of each class. Then we can calculate the posterior distribution of sample xi with the empirical offset. Note that we should subtract the empirical offset by the definition. In conclusion, our model learns the feature mean of each class instead of offset value. Naturally, the training process is very similar with the process using center loss. For more detailed about the training process, please see our paper. Geometrically, our model makes a decision boundary being drawn in the middle of each class center. We can calculate the distance between decision boundary and the class center using weight vectors and the feature mean vectors. With trained offset, the decision boundary have a different value due to the imbalanced data distribution. As you can notice from the slide, D12 and D21 have identical value by symmetry with proposed offset. Our method, using this method, it shows state-of-the-art performance in various data sets. For more experimental results and in-depth analysis, you can refer our paper or come to the QA session. Thank you for listening, and please feel free to ask any questions in the session. Thank you.